Hi, and welcome to the Computer Architecture Podcast, a show that brings you closer to cutting edge work in computer architecture and the remarkable people behind it. We are your hosts. I'm Suvinay Subramanian.
And I'm Lisa Shu. Our guest on this episode was Dr. Gabriel Loh, who's a senior fellow at AMD Research and Advanced Development. Gabe has had roles on both sides of the industry academic divide, having also been a tenured associate professor in the College of Computing at Georgia Tech. Dr. Loh is known for his contributions to 3D die-stacked architectures, memory organization and caching techniques, and chiplet multicore architectures. His ideas on these topics have influenced multiple commercial products and industry standards. Additionally, he is a recipient of ACM SIGARCH's Maurice Wilkes Award. He is a Hall of Fame member for Micro, HPCA, and ISCA, and he's a recipient of the NSF CAREER Award. And to pile on top of that, he's a co-inventor on over 100 U.S. patents. We were lucky enough to snag him for a conversation about system design for large and complicated systems like the Exascale project at AMD. We also discussed memory technologies, navigating Amdahl's law in the age of accelerators, and he dropped some unconventional wisdom about how it can be great to be wrong and when imposter syndrome can be a good thing. Before we get to the interview, a quick disclaimer that all views shared on this show are the opinions of individuals and do not reflect the views of the organizations they work for. And with that, let's get right to it. Gabe, welcome to the podcast.
Hey, thanks for having me.
We're so glad to have you. So listeners to the podcast know that our first question is almost always, what's getting you up in the morning these days?
Well, there's the technical and non-technical answers. The non-technical is just the kids and getting everyone off to school. Technical these days, I've actually switched a little bit full circle. I'm working on CPU microarchitecture, which is where I started my PhD career before going off on a smattering of all kinds of other topics. But it's kind of fun. We're back to where we started. And while for, I think, a lot of the academic circles, traditional CPU microarchitecture may not have the same flair, and it's not quite the hot topic for some folks. It's still a critically important aspect to everything we do. There's a CPU, it's still the central processing unit, even in our larger heterogeneous systems. And Amdahl's law doesn't go away even in the world of highly accelerated heterogeneous systems. And so we still need to keep pushing that CPU performance further and further in tighter power constraints. So there's a lot of exciting challenges there. It's fun to get back to it.
That sounds super fun. Yeah, I mean, microarchitecture is usually what makes all of us computer architects attracted to the field in the first place. And so there are some people who would argue, though, that at this point we shouldn't be focusing on. I mean, the age-old debate, right? We don't need to focus on microarchitecture. We should be focusing on things like, the network or whatever. And so what kind of problems are you guys at AMD trying to solve that sort of necessitates digging really deep into the microarchitecture at this point?
Yeah, to be fair or complete, it's microarchitecture. CPU microarchitecture is not the only thing that AMD is focusing on, right? This is kind of the area of what gets me up in the morning, what I'm currently working on. But we've entered a world where there are no more there's no more low-hanging fruit, or there's no single bottleneck that needs to be solved. All of the easy problems, none of them have ever been easy, let's be honest, but the easy-ish problems have been picked clean, and we need efforts on all fronts. And so there are accelerators, there's the software, and then even software is a gigantic mass of both from applications down to the runtimes, compilers, tools, firmware, etc. And modern computer systems are incredibly complex, and you need all the parts working together efficiently. If one part isn't really doing its job or is out of sync with the rest of the design, you can give up efficiency gains, whether it's performance, power, cost, etc. I think all of these areas are critically important. We have to focus on the microarchitecture. We have to focus on accelerators and new domain-specific approaches. Accelerators themselves, right? They're not really general purpose, right? The whole reason why you can accelerate things is that you're doing them in an application-specific manner, right? There's something about the domain, about the workload, that you can take advantage of to do something more efficiently, more effectively, and that's where you get the performance, power enhancements. It's sort of almost an oxymoron, right, to have a general purpose application specific accelerator. right? But what goes along with that is that no accelerator design is going to solve the world, right? We're just going to solve all of our problems, right? It's going to solve a subset of our problems. It's going to provide some great enhancements in the subset of problems. But what do you do for all of the other problems that we still have computationally or more broadly socially, whatever? And so we need, I think we're headed in the direction already of increasing heterogeneity, right? You look at the number of accelerators in mobile phones and things of that sort already. They're incredibly heterogeneous with many different functions specialized for different tasks, and you get fantastic gains in efficiency in that fashion. But what you also look at is the corresponding software ecosystem that goes with the phones, and across, again, all the different layers. It's not just writing apps for your app store or whatever, but all the way down to how the manufacturers have to put it together, all this IP and the overall methodologies. There's a lot of infrastructure, and all of this has to come together. And so the microarchitecture, I think, given my background and the things I've done, is certainly something very interesting. As you said, I think it's a very interesting topic for many folks that start off on the journey of computer architecture. Basic, how does a pipeline work? How does a cache work? And those things are so important, right? There's been kind of these old jokes about how everything in computer architecture comes down to like 3, 4, 5 concepts. It's pipeline and caching, speculation. I think there's a couple more, right? But those things, still matter, and there's still opportunities to continue to improve and refine them. I think what's also really exciting is we used to, traditionally work a little bit more in silos or, kind of within our own layers of the abstraction stack, right? Everyone who's taken an introductory, computer organization course has seen, one of these figures starting from the devices all the way up to the application with a bunch of horizontal lines in between. Right. And I think, these days, while, people talking about working across the stack and interdisciplinary research, the buzzwords have been tossed around for many years. But I think we're seeing a lot more of that, put into practice. A lot more people are talking and thinking across the layers. And that's opening up a lot of new opportunities, for the microarchitecture, but for the architecture, the ISA, and everything above. And so, yeah, our problems, our challenges are, getting tougher, but at the same time, there's, just seeing lots of new ideas every day. You look at these computer architecture conferences and the number of papers that are, being published, and the creativity and innovation that you're seeing across these works, from academia, from industry, from government labs, all manner of folks are contributing, great ideas, and we need it all because problems are just getting harder.
Great, thanks a lot for that really good context to our listeners. While we do currently live in the age of accelerators and the shift towards heterogeneous computing, it's very important to realize that system balance is very important. And as you mentioned, there's no one silver bullet solution that's going to fix all of your performance bottlenecks, especially if you care about end-to-end performance. I want to pick up on a couple of themes that you mentioned. So you talked about how we are no longer sort of working in silos, and there's a greater need and greater demand to sort of work across different layers of the stack. So I wanted to pick your brain on what are some of the themes that have sort of piqued your curiosity in this particular realm. We have a confluence of multiple trends like emerging workloads, emerging technologies, emerging architectural themes like heterogeneity, different software stacks, and so on. So what are some themes here that have piqued your curiosity? How do you think about working cross-stack in the current age?
I think one of the big challenges, as well as, I think big opportunities, is where to rethink interfaces, as well as where not to mess with things that work, perhaps, right? What is the right way, especially as we get into high levels of heterogeneity, and there's heterogeneity at different layers of the stack. The risks for kind of dealing with combinatorial explosion of how these different things interact with each other becomes, it's a potential issue that we're going to have to, collectively deal with. If you've got just all these different combinations of hardware, how are they all going to communicate with each other? How do you design those interfaces that remain efficient to those different needs, while not becoming, you don't want it to be overburdened, right? Because if you want to have a master interface that could talk to everything and everyone, it's probably going to end up not being as efficient, right? And so what's that right balance, right? And that, I think there's a lot of work to be done in understanding the trade-offs. There's going to be some science and probably a little art to it as well. drawing upon past lessons of, where things have, worked well, different standards and approaches. But there's also, new needs that have to be addressed. And so I think that's going to be a very interesting area to go through. And then another aspect of that, beyond just the interfaces, is, once you have all these different, heterogeneous components, hardware and software, you put them together, and, if things don't go entirely as planned, there's some unexpected behaviors and such, how do you test or anticipate or specify, the expected behaviors, system validation, design verification at this scale, particularly if you have, multiple different parties involved. I take an accelerator from one company and, another component from a university, et cetera. I'll put them all together. Sometimes even with a well, defined specification, people still read the specification in different ways. And, how do you guarantee that? Or, guarantee is probably too strong a word, but, what can we do collectively from a methodology and a science standpoint to make these systems, robust and as successful as possible? So I think, there's, I don't have the answers to all of those questions, but, these are the types of things that, I think many of us do need to think about going forward.
All this makes me sort of think about like the general value of understanding like large system design, right? Because earlier in your answer, you mentioned something about cell phones. And so I know when I was at Qualcomm, that we had, these are small systems, but they had lots and lots of different accelerators across them and lots of different interfaces, lots of different ways for things to discuss. And then there was a lot of discussion internally about, how are we going to model this, and how do we've got these siloed systems, and what about the full system end-to-end design? And I imagine, in all the work that you've done with Exascale, that's very similar. Where Exascale systems are enormous. You've got lots of different parts, probably spanning lots of different, as you said, even organizations that are coming together, some IP from here, some IP from there, contributors from here and there, everywhere. And so across all of these, it's a large system with lots of interconnecting components. I know you just said you didn't have all the answers, but maybe you can speak a little bit to particularly your experience with Exascale, which is one of the things we want to focus on today, is like how you bring something, that's so large scale that the word Exa is in the word to make it all work together.
Yeah, I mean, that was a really interesting, a ton of fun on that journey, right? Because when we started off on this Exascale endeavor, it was, at this point, well over 10 years ago, I guess getting close to 12 years at this point, where, we're trying to predict what this machine a decade later should look like, with, whatever we could see, our crystal balls would tell us back in the early 2010s. And that spanned, a lot of different aspects. The evaluation type of components that you mentioned is just one piece of it, right? But it's a critical part, right? Because one can dream up all manner of different things, and if you don't have a way to evaluate it and to cull down the massive design space, you're just going to flounder and spin in circles, chasing the latest shiny thing. And so what we did was, it was kind of a multi-pronged, kind of multi-resolution type of approach. Early on, we looked at some macroscopic trends, macroscopic projections, just, where did we think silicon technology would be, 10 years into the future, given various projections of, Moore's law slowing down, things of that sort. Where do we project memory technologies to be, both in terms of, capacity and bandwidth and energy efficiency, so on and so forth. So, we looked at multiple different axes and made our best guesses, and then came up with a vision for, okay, well, how could we conceivably get to these Exascale requirements, right? And Exascale requirements is more than just raw compute, more than just raw flops. I think one of the aspects that the U.S. Department of Energy really put into sharp focus from the get-go was that, this is not just a benchmark machine, right? Certainly, achieving top position on the top 500 list was important milestone that I think everyone certainly wanted to see. But at the end of the day, these machines are being used for real science, right? the vast majority of the scientists working across the U.S. national labs, as well as many international partners that get access to compute time on these supercomputers, they're not sitting there doing matrix multiplications all day for benchmark scores, right? They're running computational experiments to try to discover new things about the universe, new chemicals, all manner of science. And so delivering a machine that could actually address performance for real workloads was a very it was a common theme throughout the entire program from day one. And I think that was also very useful from the AMD perspective of thinking about a machine and not just the speeds and feeds and how many instructions per cycle you can crunch through, or your bandwidths, but really thinking about, again, as even they mentioned, sort of that the end-to-end thinking of like, what are we trying to accomplish, right? And then so having set an initial vision for, okay, now how do we get there? What are the important aspects of this machine? Again, it's not just in terms of the top level numbers, but what are other characteristics that we want to ideally see from it? Like it can handle irregular access patterns of different sorts. It's we have to think about the programming model for the scientists who for many of them programming is actually an annoyance, right? They want to do science, they don't want to sit there debugging code. And so you think about all these aspects, how do you put together? And then we sort of went through a kind of a multi-resolution, different tiers of evaluation, right? Some of the evaluation was almost really more kind of spreadsheet level, like, we idealistically, you put together all the numbers. Do we get to, the types of memory capacities or bandwidths that we want to get to? Do you get to anywhere close to an exaflop of compute? Does this thing require, 16 nuclear power plants to turn this machine on, or can you actually get this to work within a reasonable power budget? So some of that stuff, order of magnitude, you could really do kind of just pencil and paper practically. But then at different levels for different aspects of the design, we use a wide variety of different tools. In some cases, you're dealing with program analysis and going through kind of more traditional profiling of application behaviors, both on CPUs and GPUs. In other cases, you're going down another layer to cycle level simulators or system emulation. In other cases, you're doing network simulation. And so for the different aspects, just necessarily given the complexity of the problem, we have to decompose and focus on the different parts. And that helps you divide and conquer the problem from an evaluation standpoint. On the other hand, it does introduce some challenges as you try to roll these things back up together, because ultimately none of these parts are standalone, right? They all have to come together into a full system. And so then you again sort of like start bringing it back together through a mix of methodologies. In some of our earlier Exascale papers that we've published in the computer architecture conferences, we indeed showed some initial projections where those projections are coming from a very diverse mix of inputs. Indeed, some of these things are application analysis, some of these are from profile data, some of it's from cycle level simulation. And that's where you end up having to rely a bit on kind of the experience and intuition of some of the more senior folks that have been designing and building supercomputers for a long time, where they have a sense of, okay, if you put these things together, these kind of projections do make sense, or that seems really odd if we're seeing these kind of results. We don't expect things to scale in that way in this particular fashion, and that may require further analysis, digging into what's going on. Sometimes you find out, oh, okay, we had a misaligned assumptions about something, and sometimes you discover something like, hey, actually this is different, and indeed it may perform better in this fashion or whatever.
Wow, that's a really great detailed answer on how to sort of build up a large system from starting small and at the lower layers, and kind of like leafing up to a big picture of how everything goes. So one of the things that I thought you said that was really interesting, Gabe, was about relying on the sort of intuition and the experience of people who've been there for a long time. My recollection is when I first joined AMD, many years ago, even before the Exascale stuff started, just being sort of in awe of the people who were able to imagine projecting, roadmap things 4, 5, 6, 7, 8 years ahead, and just being able to anticipate what they felt like was coming down the pipe. And So, in putting together that kind of a team at AMD, it's been an incredibly successful long-running project. I'm curious to see about like how you sort of project forward, presuming you're one of those people who was like doing the projections for it, you and like Mike Schulte and other people that I remember looking forward. And then also, how and when you decide you're going to say pivot, like, oh, we might have been a little bit wrong about this one, or something has changed, sort of keep the shift moving forward, because that's the hard part, right? You want to be able to look far enough ahead to do something meaningful that's in advance, but at the same time, you have to be able to adjust.
Yep, that's a great question. Or there's a couple key aspects. It sounds very Spanish Inquisition-like. So first is that you have to be in communication with other folks. As researchers, we cannot live in an ivory tower and just come up with our own big thoughts and drink, coffee and eat donuts all day. And, a critical aspect of our Exascale research program was that we were sharing our ideas, getting feedback from the folks on the product teams, the folks planning our roadmaps, getting good critical input on things that they thought might pan out, things that they thought were risky, things that they thought we were way off in left field on. And what also goes with that is you need to have a team that can put ego aside, right? That we don't get too married or emotionally wedded to our ideas, right? These are kind of ideas we came up with, but if we get good feedback, we get new input, hey, you have to be willing to throw things out and take that input and shift and pivot, as you said, right? And we, the fact that, yeah, I thought I had a good idea, this seemed really cool to me, and then now I found out that, okay, wait, that doesn't make sense anymore. I have to be very objective and just take that information in and just, okay, that's great input. Let's go figure out what's the next thing we should do. What's, how do we adjust this? How do we address those concerns? And so part of the success, I believe, for our program is that we had a phenomenal team, not just from a technical standpoint, but in terms of the personalities and the lack of ego and really this shared vision of how do we collectively build something successful, right? And that objective was shared not just with the research team, but with the product folks as well, that we all collectively wanted to see this happen. We wanted AMD to be successful. And so there was not really like research versus the product team, us trying to sell them on something, them trying to pull us back or whatever. This really is about coming together as one company, as one effort to figure out what's the best way forward for this, right? And so that also, I think, made it really fun, right? Because we just, at that, once you kind of establish that kind of culture, you no longer have that fear, really, I think, of throwing out what may be crazy ideas that other people are in some other context might, laugh you out of the room for, right? And I think, perhaps it's speaking from a position of, privilege, of seniority and such. But, I've hit that point in my career where I really don't care, right? I mean, the sense that I can say, I can put out ideas, and if it's not a good idea, if someone has a good reason why what I suggested doesn't work, like, that's okay. It's okay. I'll move on. I'll move on to the next thing, right? In general, what I feel like is that being wrong is actually a good thing, right? Because if you're wrong, like, why were you wrong? You had some intuition, some thinking that led you down a particular path, and when you find out you're wrong, that meant that there was something in your intuition, something about your assumptions that wasn't correct, and it's a learning opportunity, right? So if I'm wrong, I'm going to learn. And in some sense, if I'm not wrong on occasion, that means I'm not learning enough. And also, especially as researchers, that may be indicative that I'm not pushing aggressively enough either, right? Part of the role of a research lab is to push the envelopes, to try to push on the frontiers. And if you're being too safe, you're actually not really doing your job, I think, at least in the industrial research context, right? And it's a careful balance, right? You can't go too crazy, otherwise, you come up with, ideas that no one will ever use. I think there's a natural pull factor that brings you back to reality, right? Because so long as you're learning and taking in the new information, your ideas are going to get refined, they're going to get better, and they're not going to go, they're not going to continue diverging out into some area that's not going to be useful.
Right. That's a very germane point on the importance of culture and being able to sort of fearlessly explore ideas, recognize when things are, when your assumptions are wrong, and then pivot and, take your learnings forward and move to a different problem. I think that's a very, very important point in large teams, especially. I wanted to expand on some of the, I think a lot of the retrospectives that you've written, both on the exascale computing journey and some of the other things that you've done, have been pretty refreshing about the lessons that you've learned, what were the initial assumptions, how the field overall has evolved. Because when you start out, you don't know how things are going to evolve, both on the technical front and perhaps on other fronts like the commercial realities as well for various technologies. So I wanted to dig a little deeper on maybe memory technologies in particular, since you've had experience with multiple kinds of memory technologies and have seen different trajectories for them. So ranging from 3D die stacked DRAM, that eventually went into like hybrid cube or HPM and things like that, to other technologies that have maybe not panned out to a commercially successful point yet, like NVRAM, phase change memory or resistive memories and so on. Can you maybe sort of compare and contrast the journey and considerations with each of these? Maybe lend some flavor on how you were thinking about the problems, what are some ground realities, and how that sort of shaped your perspective on memory technologies and other technologies in general, how they intersect with both research and product roadmaps.
Sure. I think there's a couple general trends we could probably draw out from this and just thinking back. Much of my 3D related research started back when I was still academic faculty. I think especially in academia, you have the license, perhaps the charter really to push even more aggressively than one can in industry. And at the same time, frankly speaking, your levers for direct commercial impact are far weaker from academia. Right? You publish papers and try to influence the thinking of other people. From that perspective, early on, I didn't worry too much about the commercial. It's not the commercial viability of any of these technologies, but it's more about the timeline of it, right? So you talk to the folks in the industry, you get the best information you can to have the best assumptions for the research. And then from there, I would encourage, especially academic researchers to not worry too much about, well, okay, is this going to impact, industry, in 2 years, 5 years, 7 years, et cetera? Because there's just too many factors that go into it. I think what's important is that kind of the way I approach a lot of this is to come up with ideas that, assuming this technology hits a point of maturity, then these ideas would allow one to make better use, hopefully, of that technology in some fashion. And maybe it was a little bit of wishful thinking as an academic, right? But I think part of the rationale was that if one can demonstrate additional ideas, additional benefit of these new technologies, that may motivate industry to try to accelerate the development of that technology as well, right? I think from an industrial standpoint, there's still a similar theme, a similar approach, in that with any kind of new technology that we may be looking at or considering, we do want to think broadly of how would we be able to maximize the value or competitive advantage we could get with this new capability. Because it kind of goes, it's not like a one-way street, because if you come up with that big new idea, indeed that may motivate the powers of that be to try to accelerate the availability of that capability, right? On the other hand, if people aren't doing the research as aggressively enough, if everyone is waiting for a memory technology to hit a certain point or whatever, then the natural kind of cadence of that progression, or because the investment made into that new technology may not be as great, because they don't have that big motivating factor of, oh, if we can get this to market, there's this 3x, 10x or whatever benefit, right? And so there's a little bit of a give and take, right? And as a researcher, if you go too far and like the technology is still 25 years away, that's also a challenging sell as well. So there is a bit of a balance to be had there. My overall thinking or approach, it's been very interesting watching these different technologies develop over time, because from the perspective of a technologist, and things you've thought about and worked on, like, you want to see this stuff become reality, right? You want to see whether it's a new memory device, 3D stacking, et cetera. These are all things that you've worked on, you've thought about, and it's just like, wouldn't it be cool to see that in a real product, right? And some of the 3D stuff, I mean, it's taken nearly 2 decades for us to really see these things come into kind of full commercial capability. But on the other hand, as someone who works for AMD as a shareholder, and I think this is true for all of most of the companies out there, if we can make use of our existing capabilities and we can delay the adoption of some risky new technology for another generation, it's I think always a worthwhile question to consider. Well, should we actually take on that risk of bringing on that new technology now, today, right? And so there's that timing question of these new technologies may in fact have great merits, but we might not need to do it right today at this moment, right? And that's, I think, just the types of questions that are being asked by everyone in the industry at any point in time. When do you adopt, when you introduce a new capability, a new feature? Is the market ready for it? Is the ecosystem ready for it? And it's a tricky thing. I think that's more in the realm perhaps of folks with the MBAs and whatnot. Right. If you jump into the water first, you have the first mover advantage. You get a head start over everyone else. But if you jump into water and the water is shark infested, guess what? You're also the first one to get chewed up. So what's the right strategy for that? It's going to be different in every case. But bringing it back to the research side, right? There's a lot of those things are kind of well outside the realm of what your typical technical researcher is really going to think too deeply about. And you should have some awareness of these things, right? That's just, I have a great idea, then everyone's going to come to me and everything's going to be great. Everyone's going to adopt my idea and run with it, right? That's not typically how new technologies get developed. But at the same time, especially as an academic researcher, I think if you try to read the tea leaves too much, it's going to be a kind of a distraction, and many of those things are kind of outside your control. And you really should, in my opinion, focus on the technical innovation. What are the new ideas? What are new capabilities? What new can we collectively do with this? And that, if anything, I think would help accelerate the adoption of new technologies faster than the business concerns. I mean, the business concerns obviously remain, but if there's sufficient motivation, if there's sufficient benefit or value, I think industry will find a way to capitalize on that.
That was a really interesting discussion, because it sounds like you're basically discussing the chicken and egg issue that we have with new technology adoption, right? Is it sort of the push pull where the researchers are saying, hey, look, if you do this, it can be 10x, and then of course industry will come by and say like, well, after you put in some reality, it'll become 1.8x or whatever. But then there's that part where there's like, hey, if you do this, it'll be this great new thing. And on the other hand, there's the whole Henry Ford's quote, are we going to build better horses? Or are we going to start building cars? And so there's that question of like, when do you make the jump to making cars and then stop, like, I don't know, feeding your horses better food or whatever. So that whole discussion there, that was like so interesting, because from a researcher's perspective, particularly a younger one, there's only sort of like the immediate problem around you. And as you get more senior, as you presumably, or as you are now, you begin to have to think about market forces potentially more and more, because then your impact is sort of dependent on whether or not things really get adopted, right? And so this kind of ties into the next question, which is, you're at AMD Research, which is actually a relatively new lab, and which has been phenomenally successful in going from a handful of people 12, 13 years ago to being this like sort of very effective research organization that has close ties to its product team, as well as it had a lot of research impact. And so I guess what I wonder, in an era where research labs sort of ebb and flow and kind of struggle between being those researchers out there who can't get any product people to listen to them, or being too in bed with product people and not really doing anything particularly far reaching and out there, how do you feel like AMD Research Labs in particular has sort of gone from this tiny little group to this really sort of research powerhouse that's been really effectual from both the research as well as the product impact standpoint?
I think a big part of that is always being clear with what the purpose of the lab is, right? From the get-go, the research organization was focused on the fact we're very honest and truthful about it, right? We are part of a for-profit company, and what we do ultimately in some form or another needs to deliver value back to the company, right? Is for each individual, for the organization as a whole, are we providing more value to the company than it's costing us to keep us employed? I mean, that's kind of what it all comes down to. But that honesty of your role in the organization, I think, helped to really provide the focus that, a lot of research, it's almost, cliche that for, you tell this for a lot of, PhD students and others, is that, defining the problem is often the hard part. How do you select the right research problem? And once you've defined the problem, people are smart, they can come up with solutions, they can innovate, right? And a lot of the times coming up with the right problems is at the first, almost unspoken step zero. Having clear direction for the organization provides us a framework for prioritization of all the different ideas that we could pursue, all of the different research projects that one could imagine. We don't have enough bandwidth to go after every possible thing, right? I mean, that's true whether in academia or in industry, right? No one has, or most of the time, most professors don't want to have a lab of 30 students. It's we all have enough meetings as it is. And so, how do you prioritize? How do you go about choosing where to focus your effort, where to make your investments? Clear direction in terms of having to do research that will provide value, will have impact to the company, I think is central to why the lab has been successful. And that said, as you mentioned, it's a balance, right? You don't want to be in a position where you are effectively just additional engineering resources for the product team, right? That as a research organization, you do need to be looking further down, down the field, and you do need to have that autonomy to take some risks and to push it further out. And so, I think part of it is having good leadership that has been able to walk that line and strike that balance, right? That we have to have work that's not just ivory tower, pie in the sky, interesting, intellectual exploration. But at the same time, you can't be really just doing almost, just advanced development for, some features that the product team perhaps, didn't have the resources to pursue. And that, I think, it ebbs and flows over time as well, right? And I think that's where, the leadership, both in terms of the management as well as the technical leaders, and them having a good relationship where management can get the right technical input, they can get the right business input, everyone can talk to each other, again, kind of in very ego-free, just what's the lay of the land, what are the best decisions for the organization, and to be able to come up with those decisions of where do we place our bets. At the end of the day, we are still speculating. It's it's the future, we're doing research, but you have to put the chips down somewhere, and hopefully we've collectively brought in as much information together to maximize our expected return.
No, that was a good perspective on how you think about research labs within the context of an industrial setting, and having a very clear sense of purpose and vision coupled with a healthy culture that's ego-free and transparent makes a lot of difference. Maybe this is a good time to sort of wind the clocks back. Since you were talking about AMD research, can you tell our listeners, how did you get to AMD research? What was your journey like starting from the early days? Because you've both seen academia and industry. Maybe you can talk about the entire journey.
Sure. This is I've been very fortunate in that I've had just a lot of different opportunities along the way, and I think one of the interesting aspects is that, and a lesson for some of the younger folks, is to not be afraid, or you'll be afraid. How you feel is how you feel, but despite perhaps being afraid, being unsure, still taking some of those chances on unexpected paths and routes. And because I think my career has taken a couple weird turns over the years, really starting off from the beginning. After initially when I was finishing up my PhD, I kind of finished off a little bit weird on the job market cycle, and I'd been originally wanting to pursue an academic position, which is what did happen. But my first time around on the job cycle, I actually ended up with one interview for a position that might or might not appear. It was a speculative interview from a department that was hoping to get a slot created that year, and in the end, they didn't get the slot. And so I had, basically zero academic job offers at the end of that first cycle. Kind of thankfully, or the way it worked out was that, since my my PhD graduation or completion was like a little bit off cycle, that I was able to kind of just stay on as a student for a while and maintain my health insurance and things of that sort, and then was able to reapply the following year. And I had some other papers and things in the pipeline at the time, but the second time around things were more successful. And so one thing is that certainly we all face rejections and failures of sorts, or as people like to say, deferred success. And if it's something that you believe in, you want to go for, stick with it, go for it. Again, maybe a little bit of survivor bias in these comments here, because I was lucky enough to get an offer on the second time around. But in terms of kind of unexpected routes, one of the things that came up was I'd already received my offer, and actually for going to Georgia Tech. And at ISCA in 2002, this was up in Anchorage, Alaska, I just happened to meet this guy, Brian Black, who those who are familiar with die stacking kind of know him as the godfather of 3D die stacking. And he was working at Intel at the time, and he said, "Hey, you should just come down, work for me for a year, learn a little bit more about things on the industry side or whatever." And basically that sounded interesting. So I was like, okay, wasn't what I was planning at all. But I went back to Georgia Tech and asked them, like, hey, like, is this like something we do? Can we like defer the start of my academic career? And it was a little bit complicated in terms of the paperwork and everything else, but we basically managed to come up with an arrangement where I basically joined Georgia Tech and went on a leave of absence on the very first day. It was kind of funny because I had already then started, once we made the arrangements, I'd already started at Intel, and I had to fly back to Atlanta to like sit through orientations on like 401k programs and things of that sort. But the thing was that like it wasn't like a normal path at the time. I think it's become a little bit more normal now, but the lesson that I learned was like, don't be afraid to ask, right? Because if you don't ask, you're not gonna get it. And so I asked, and we found a way to work through the situation, and we got to work. And this and that was pivotal, right? Because it's at Intel was actually where I first became exposed to 3D die stacking, right? And honestly, just dumb luck. I was at the right place at the right time, happened to be exposed to the right people and these new ideas. And part of it is that when you have the opportunity, you got to take advantage of it as well, right? So I kind of subsequently, after going back to Georgia Tech, that became a cornerstone of a lot of the research agenda I put together. But I honestly got incredibly lucky that I just happened to be in the circumstance. But that circumstance also happened because I was willing to take this weird detour on my career. This is year one of my career post PhD, and already kind of going off the planned path. But that can provide new opportunities, new things that you learn about. Another example of that, after several years in Georgia Tech, there's a new program that was just being started. It was a dual master's program between Georgia Tech and Korea University in Seoul, and they needed a couple of faculty to go to Korea for one semester to teach in person. And so they're kind of looking around and a little bit desperate to figure out like who to send, and they came and asked if I'd be willing. And I had some hesitations, right? As I was my partner would still be working from Atlanta back at home. I'd be over in another country for 4 months where I didn't speak the language or anything, but it was also just kind of new and different. And so at a certain point I said, well, why not, right? Like, when is this kind of an opportunity going to come up again? And so I did it. That then opened up, again, just sort of by luck, circumstance, whatever you want to call it, a variety of new opportunities as well. Right? I think on one hand, from the academic side of things, that basically was the first step that eventually led me to actually being co-general chair for ISCA 2016 in Seoul, Korea. Like, that just would not have ever have happened had I not spent those 4 months in Korea.
I've just got to jump in here, Gabe. And so being general chair of an ISCA sounds like a tough job. So I'm going to assume that you regret going to Korea. Because if you hadn't, you wouldn't have been general chair and had to go through all that stress, right?
I think different people, everyone's different, right? And so like, yeah, general chair was a ton of work, but for me, it was also fairly rewarding. This computer architecture community has been very good to me over the years, and it felt good to be able to contribute back and give something back. It was definitely a lot of work, but it was very different. So I mean, I know some folks, especially a lot of academics, look upon general chair as something that they would not touch with a 10-foot pole, because there's practically zero that's technical about it. To some extent,
on top of that, you did it not in your home locale. Like most general chairs do it in their home locale. You did it on the other side of the world, which probably adds a whole other level of complexity to it, which I'm just like in awe that you did.
Well, I mean, as with everything, and this is I think a common theme, right, is that you have to have a good team, right? Everything we do, whether it's research, whether it's putting on a conference, having a good team, having the right relationships and trust among the team members is absolutely critical, right? That could not have happened without having had a phenomenal co-chair. My co-chair, Professor Sungwoo Min, who unfortunately passed away a couple years ago from cancer. But he was just a phenomenal partner, and we were able to again have very open discussions. He actually came not traditionally from the computer architecture community; it was more from the embedded systems side. And so we had a lot of good discussions in terms of conference expectations and how what types of events and venue styles and things of that sort. And he was very open to listen about how we did things on the ISCA side, but there's a lot of things that were local about how they do things in Korea that I could not come in and assume I knew how things should be done. Right. And both of us, being able to put egos aside and really, again, thinking about like how do we, we both had a shared vision of, how do we put together the best ISCA ever, right? I don't know if we did or not. I'll let the attendees vote on that perhaps, but that's we kind of again, you want to start off with a vision for what you want to accomplish, right? And once you have that vision, then you can kind of drill down and work through what do we want to do from a technical standpoint? What do we want to do in terms of the events, in terms of venue, about the experience? For a lot of attendees, this was the first time they'd ever been to Korea. What do we want to showcase and highlight about the country? And we just kind of just drill down through all of the different details. And for me, the way I looked at it, and why it wasn't just some horrible burden, but it was actually I think somewhat fun and rewarding, was that I viewed it as, hey, this, the computer architecture community is, at least from an academic perspective, my home community. I'm now in a position where I could throw a giant party for, 700 of my best friends, and I don't have to pay for it. What can we do, right? And, and that's kind of the way I viewed and approached it. And it's like, how do we, make sure that this is a great event, technically, but also that it's memorable, that part of it is the community building, right? We want people, especially a lot of the students, maybe this is their first time come to a conference, right? Maybe they went to another conference that, they, didn't enjoy as much for some reason, whatever. And they're, maybe thinking about, changing to another area or something. How do we give everyone a great experience so that, this is where I want to be, right? I want to be a computer architect. This is, and if I have to bribe them with some good food or something like that, hey, that's okay, right? Human resource development, if it goes through the stomach, that works,
I've heard that's how they turned around micro in the early days, right? They made sure they had good food.
Well, I mean, you go to any like college recruiting event or anything else, right? Just food features prominently, right? The students tend to respond to free food, and then once you've trained them, that habit doesn't seem to go away.
Well, I wanted to ask you a little more, Gabe, because, so I've known you a long time. And one of the things that I've always noticed about you that's kind of remarkable is like, I've never seen you perturbed. Like, I've never seen you angry or perturbed or anything like that. And one of the enduring themes through you talking about with us today has been about like being able to put ego aside, having a shared vision, a clear vision for what is going ahead. So one of the things that I've always thought about you as you've sort of progressed through your career is just like, you make it look very easy, right? You've always made everything look very easy. That's one of the things that I remember when I worked with you like a long time ago at AMD, is just that you have this talent for being able to just say like, okay, this is what we're trying to do. This is how we frame the problem. We need to answer this, this, and this. And then you just go do it. And then like, you know, you just kind of, it seems very self-evident as if somebody's watching you do it. And so it seems like for the progression of your career, which, you know, you've been very successful, is, you know, being able to put ego aside, being able to construct good teams with good culture, having clear visions, and this thing which just I'm observing about you is like you're this kind of unflappableness. Can you talk a little bit about what you think it is that has led you to this? Because I also remember when I first met you, you were already faculty at Georgia Tech, and let's just say that your behavior, I thought you were still a grad student because you were still like fun and easygoing and all this stuff. I had no idea you were already a professor, which meant like you'd already done your time with Brian Black too. Like you were a couple years out from graduation. And I was like, this guy is definitely a grad student. And then you were a professor, and I was like, oops, yeah, I made a wrong assumption. So maybe, you know, I don't know, just going back over your career from like how you manage yourself over the course of career to get to the point where you are. It sounds very clear that you haven't chased career accolades. You've just sort of chased what interests you, and then the career accolades have come. Can you maybe talk a little bit about that?
Sure. And I think, you know, in terms of, you know, do I have my stuff together and, you know, unflappable or whatever, there's, you know, I think it's really important for everyone, especially for the younger folks, but this doesn't go away with time, I don't think, is to, you know, always recognize that what you see of other people is very different from what they are experiencing, right? Each and every one of us has a mask, has a filter, right? You don't, you know, whatever things that didn't work out for me, whatever challenges I had, you know, it's typical human nature that you know, shield and you filter these things out from everyone else around you, right? And so, you know, were there challenges along the way? Absolutely, right? Do I go necessarily advertising all of them? Probably not, as you know, most people tend not to, right? There's this old saying that, you know, when you look at everyone else, what you see is the movie trailer, right? You see all the highlights, the big, you know, Michael Bay explosions or whatever. When you look at yourself, you see the blooper reel, right? You see all the outtakes, right? And it's actually one of those things that I recognized this at some point, and that recognition alone, I think, was very useful in terms of, you know, not getting too shook up about, you know, challenges and things of that sort. Because when you look at everyone around you, everyone else looks like they're so successful and everything else, right? But then when I realized that, okay, well, this because they're not showing me their outtakes either. I'm not showing them theirs, and so why should they show me? You know, that's only fair, right? But once you realize that there's that kind of this asymmetric information access about what you know about yourself versus what you know about others, it's easier to be easier on yourself, really, right? And so I think that helped me in terms of, you know, some level of that, you call it unflappableness. I don't think that's quite accurate, but, you know, some emotional stability perhaps, right? In terms of just worrying about, you know, what's going on in one's job, in one's career, or one's research, whatever it may be. Certainly everything that we do is also viewed through a lens of survivor bias, right? For every, you know, paper that I've published, for every, you know, project that's been successful, you know, there is a gigantic heaping pile of rejected papers, of ideas that crash and burn and everything else. And, you know, I don't put them up front and center, and like neither do most other people, right? But again, you know, we all see the stuff that makes it. We don't see all the stuff that, you know, that didn't make it, but are still important stepping stones to get to that point, right? Of, you know, how do you refine and adapt your ideas? What are you, you know, learning along the way? And another kind of thing that I've learned over time, and it's one thing to, you know, intellectually understand it, it's another thing to be able to emotionally accept it, is being able to recognize what things do you have control over, what things are outside of your control, right? Because basically to get upset, get worked up, anxious, whatever, about the things that are outside of your control is pretty much by definition a waste of energy, right? Because they're outside of your control. Anything you do is not going to affect that. And learning to recognize those situations, those circumstances, it's taken years, and obviously, you know, no one perfects this, and it's something that I still work on. But, you know, learning to recognize those situations and then be able to take a step back and sort of to emotionally diffuse yourself a bit, and then then rechannel your energy on the things that you can do something about, that you can be productive about. That has also helped. But that's, this is something that's taken, at this point, decades worth of practice, and obviously, still not entirely there. It's, I don't think something that anyone can perfectly achieve in a lifetime, but one can continually improve. So I think that's also been just kind of a practice that I've kept in mind over time. Another, I think, really important aspect of this, and again, I think it's important for some of the younger folk. Again, it's related to that whole the bad analogy about the movie, outtakes versus the highlight reels. But what often comes up in these types of discussions is a whole like imposter syndrome type of thing as well, right? You look around, you look at all like the senior people, and like, oh my God, like like you never see any of them having imposter syndrome, right? But the fact of the matter is everyone does. Again, but we don't show it, right? It's buried in our outtakes reel. And initially, it's one of those things earlier on in your career, I think, kind of hits you a bit harder, right? You're thrust into new situations, and you're just like, oh my God, like, why did they ask me to do this? I have no clue what's going on. I'm going to fail miserably, et cetera, et cetera. Like all the standard imposter syndrome thoughts, creep in. But one thing that I've learned over time, and it's helped with these types of situations, is that the reason you have imposter syndrome, the reasons may be too strong, but one of the factors of having imposter syndrome is that you're actually being put into new situations, right? It's because you're being challenged. People trust you and are giving you opportunities to grow, right? And so it's kind of flip side of it. If you never feel imposter syndrome, you may be stagnating, right? You may be in a place where you're not getting the opportunities, right? And so to me, imposter syndrome has now become a somewhat positive thing, or at least I tell myself that, right? Because it means, okay, I'm in a position where I'm going to do something new. I'm going to learn, right? That someone trusts me with something new, right? So like, it's actually a sign that things are going well if you have imposter syndrome, right? And again, I think a little bit of this may be just me trying to convince myself to make the situation a little bit easier to handle. But I think there's some truth to that, right? Like if you're just always comfortable, that means you probably are not growing on the trajectory that you potentially could be going at. So I mean, a lot of it also comes back to your original question. How do you keep it all in check and whatever? It's like, you don't always. You don't always, but I think most of us have learned to filter and at least hide it out a little bit, right? That's just human nature. But that said, there are ways to improve how one handles it over time, and how to focus your energy on the things that will be most productive, that you do have some control over. And I think that's worked reasonably well-ish for myself over the years.
Yeah, that's great. Thanks a lot for that perspective, Gabe, and also very valuable words of wisdom, I'm sure, for young researchers and people further along in their career. Speaking about focusing your energy into the future and so on, maybe can end on what's on the horizon for you. What's your vision, both on the technical side and maybe also in terms of how do you build up our community further? Because that's one of the things that you've been really good at, sort of mentoring and community building. So both on the technical side and the community side, what's on the horizon for you? What is exciting for you? What would you like us to see more, do more of?
Yeah, I mean, one of the things from the technical side, and I think the computer architecture community has been pretty good at this, and I really want to encourage especially those in positions of whether it's program committees or funding, research grant proposals, things of that sort, is to continue to keep a broad mind, a broad definition of what computer architecture is. Right, I think we've had everything from the traditional CPU microarchitecture all the way up to the data centers, and now machine learning systems, and all manner of different things, and keeping that very broad perspective and a very broad or loose definition on what is a computer, what is architecture, has been very good for this community. It's allowed us to grow, to adapt. The technology keeps changing at an incredibly fast pace, and if we get overly narrow, overly prescriptive of our definition of what is and isn't computer architecture, I think we risk becoming irrelevant over time, right? If that definition misses, you may miss the boat on some really impactful areas that other communities may take and run with. And so I think from technical perspective, we want to keep our view very broad. And as we enter the twilight of Moore's law, it's in some sense kind of exciting in that it now forces our hand into looking at a more diverse set of solutions, right? And we are working across these different, we talked about it earlier on, of working across the stack, being more interdisciplinary. And part of it is like abstractions are not bad, right? Like they're good, they provide productivity. And traditional Moore's law, it was actually, I think, better to have cleaner layers between everything, where everyone can kind of work more focused in their layer of the stack. But we're now in a world where we cannot continue to scale traditional performance and capabilities of our systems in that approach, right? So we just have no choice, really, that we have to work in a broader, more collaborative fashion. But that's, again, I think very exciting, right? So many new things to learn, right? I mean, when I joined AMD, the bad dad joke was that I couldn't even spell HPC, right? And the time I had with the Exascale program, I learned a ton through that process. And a lot of what I learned was not perhaps what you would call traditional computer architecture, right? But that helped make my computer architecture, thinking better. For myself personally, with all of the new stuff coming along, and of course, machine learning is taking up a lot of the attention, but there's all sorts of other fascinating topics that as you learn more about, it expands your mind and can help you think of new solutions, new approaches for even the more traditional problems that many people may be working on. So I think from a technical perspective, I do see increasing heterogeneity, increasing end-to-end thinking of design. Even if my day job is still looking at CPU microarchitecture, I'm still thinking about these things in a much broader context than I perhaps would have 20 years ago, where everything was just how do we optimize spec 95 or whatever. It's a different world, but for the better. From a community standpoint, I think it echoes a lot of that, right? We're going to see our community continue to grow. I do think it's vitally important for the computer architecture community to continue to increase access to to everything we do to more and more people, right? It's just very competitive in terms of trying to attract and recruit talent into our master's programs, our PhD programs, et cetera, right? There's a lot of people out there that are looking at many different other computing topics. There's a huge amount of competition with the software world, even as software and hardware become more intertwined. And to me, that says we have to maximize accessibility to everyone, and that's across all different types of factors, right? So there's all the dimensions that get the greatest attention in terms of gender and ethnic makeup, but there's also socioeconomic. Are we really making the best usage of all of the different universities we have across the planet? There's talented people everywhere. Are we getting everyone into positions where they can succeed and contribute to what's just becoming harder and harder technical challenges and problems? And it kind of goes back to the comes to the ego comments, right? Like none of us should think so highly of ourselves that this some small cadre of us are the ones who are going to come up with all of the answers for the next 10 to 20 years of computing, right? The next big idea, or the handful of medium ideas that often actually make things move at a faster rate than the big ones, which sometimes can be more controversial. Those could be coming from all over the place, right? From all over the planet, from all types of people. And so really making sure that we can get that next generation of computer architects identified and excited, fed if need be. I think that's a really important aspect of the community. The community is the people, right? We are the community. And last I checked, I keep getting older, so we need to recruit.
You don't look it, Gabe.
Younger
You
folks.
don't look it.
That's only because I shaved my head. When I started shaving, I discovered it stopped my aging, right? Because my hairline keeps receding, the hair keeps turning gray, but no one can tell.
Yeah, you look the same, and it's been over a decade, and you're indistinguishable from your early photos. Yeah, early photos, and how I remember you from the early days when I thought you were a grad student. I mean, this has been a really, really wonderful conversation, Gabe. I think we've spanned, from technical to career to really sort of like kind of deep thoughts about how to think about ourselves and the community. And so we really appreciate you coming to talk with us today. And we're so glad to have had you.
Great. Thanks a lot. This was a ton of fun.
Yeah, thank you, Gabe. It was a real pleasure talking to you. And to our listeners, thank you for being with us on the Computer Architecture Podcast. Till next time, it's goodbye from us.